students, Mr. Keister here with you. We are in Unit 12.1, Kinetics and Reacts. And today, to hopefully finish up and talk about activation energy. What it is and how it's determined mathematically. Behind me here, you can see it. Now for I've been in school this time. Today we've been in April 7th. However, these are not correct anymore on and of course will be semester. And so please refer to your house document now my calendar from my home campus. For those who watch this, have been doing some about 3 or 4 behind and 2 to e-learning. I believe for Chem 2 lesson is somewhere the 8th of May. I remember correctly. Would be a date a little bit. And in honors, actually, the lesson would have occurred after the end of our school term, still providing you access to it. On next and our final unit 2 on each. Those are topics that you are going to know or your class. View and Chem 2, I have the same sentiment. Unit 12, probably a date for the semester. I'm still going to do those lessons as well as that topic. With chemistry. So ahead. Here. And let us now pull up our notes for today. And there they are. So, activation energy. So, in 1888, the Swedish chemist Svante Arrhenius, remember Arrhenius was one of the acid-base theory people we talked about in Unit 11. The Arrhenius theory of acids says that solutions that release hydrogen ions are termed acids, and solutions that release oxide ions are called bases. So he was involved in acid base as well as in regard to activation. So he in 1888 that molecules must possess a certain minimum amount of energy in order to react. In other words, they have to collide with one another at a certain speed with an amount of force in order to react. Again, this comes from the collision model, so that energy comes from the kinetic energies of the colliding molecules. So the collision model is based on kinetic theory, which states that molecules must collide then in order to react. The greater the number of collisions occurring per second, the greater the rate of the reaction. Okay. So this coincides with concentrations of reactants and their effect on rate, which we've talked about multiple times in the Unit 12.1. And that is the greater the concentration of reactants, the greater the number of molecules that there are of reactants, and thus the greater number of collisions, which then, of course, would increase the rate of the reaction. So upon colliding, the kinetic energy of the molecules is then used to stretch, bend, and ultimately break bonds, which will then lead to a chemical reaction. So in order to react, colliding molecules must have a total kinetic energy equal to or greater than some minimum value, and that is called their activation energy. Energy can be evaluated mathematically. The rate of reaction at different temperatures. Keep in mind, as we've already discussed, about a rate constant. So each chemical reaction has its own specific value of a rate constant. Okay, and yes, and in our last lesson on rates, we learned how to determine the value A from experimental data. And so what you have to understand, though, is that value of K is constant only at a specific temperature. When you start changing the temperature at which the reactions run, or you change the speed and thus the kinetic energy of the particles involved in the reaction. And so that is going to affect the speed at which the reaction occurs, the rate at which it occurs, and thus the rate constant. So although a rate constant is indeed what it says it is, constant for a particular reaction, that rate constant can vary at different temperatures because of the speed and collision force of the molecules involved. So this is called the Arrhenius equation, all right, and is used to calculate EA, which is activation energy. So this is activation energy right here. All right, and so this is the natural log of this ratio of rate constants at two different temperatures. This is a small k, which we have learned how to determine mathematically. So those are the rate constants at two different temperatures. R is the ideal gas constant. And that we use its kPa value, which is 8.31 in the Arrhenius equation. That's what normally is used. And then we have 1 over T2 minus 1 over T1. And again, this is the temperatures at which these constants are determined. So T2 is the temperature at which the rate constant has a value K2. T1 is temperature at which the rate constant is a value K1. And so these T's are in Kelvin, of course, as they normally are in our calculation. So let's go on to the next page here. So now we're going to use the Arrhenius equation to determine the activation energy for this reaction. Here. The temperature of the rate constant for the following reaction is calculated below. So again, this was determined from another data table whereby we took the concentrations of our here and varied them and was able to determine not only the rate law but the value of the rate constant, and that was done, as you can see, at 5 different temperatures. And so the rate constant again does vary with temperature. And so we calculate the activation energy for this reaction. Okay, so before we even do this, so first of all, note that these temperatures are in Celsius, so we're going to have to make an adjustment there to get in Kelvin. And notice here also that the rate constant unit is given as m to the minus 1, molarity to the minus 1, seconds to the minus 1. So I guess just as a quick review from what we talked about in regard to rate constant and the value of its unit is based on this: what order overall is this reaction? So without even analyzing the data in regards to concentration, varying concentration of the two reactants and determining a rate law, without all that available to us, can we still determine what order this reaction was? And the answer to that is yes. If you look at the unit for this rate constant, remember we had a little short, I showed you how to do this the other day, but we also then ended up by showing you a shortcut as to how to determine the unit for the rate constant. And that is by looking at the value, the absolute value of those two exponents added together. And if you take -1 and -1 and add them together, the absolute value of that is 2. And so this is a second order reaction. Second order. Now, there are two reactants here. So basically, there's one of two possibilities. If each of these reactants could first order, that's definitely a possibility. Or one of them could be second order and one could be zero order. Either way, that can give us an overall reaction order of 2. We don't know that without looking at the actual rate law data. But we do know just from this unit that it is second order overall. So down here, let me raise this up a little bit. There we go. So here's our data. Again, first things first. So basically, we are given 5 pieces of data here. 5 pieces of data. First thing is, in regards to the Arrhenius equation, our temperature has to be in Kelvin. So let's do that real quick. So let's add 2, 3 to each of these, so we can get our T's in the correct unit. And so the first one is 600K. Got it labeled up there. And then 650, 700, 750, and 800. Okay? So keeping in mind then, let's write down the Arrhenius equation. So the natural log of K1 over K2, all right, is equal to activation energy over R times the quantity 1 over T2 minus 1 over T1. So we need 2 pieces of data to run through the Arrhenius equation. So I'll make a little note about that over here. So we need 2 data points. Will it matter which 2 we use? No, it will not. And so I'm just going to go ahead and pick the first 2. And we'll go from there. All right. So the natural log of K1. So K1, our first one would be 0.0280. And our second one would be 0.220. So the natural log of the ratio of those 2 numbers equals EA over R times. Okay, 1 over T2. So T2 in Kelvin is 650. So that'd be 1 over 650 minus 1 over 600. Okay? All right, so I'm going to take this ratio, 0.280 divided by 0.22, natural log of that answer there. Not going to do any rounding yet, of course. That comes out to be negative 2.061423036 equals EA over R is 8.31, and 1 over 650 is 1.53, 8461, 538 times 10 to the minus third minus 1 over 600 is 1.66 repeating times 10 to the minus third. So if we subtract these 2 numbers, we get negative 1.28, 20512, 8 times 10 to the minus 4. All right. So we are going to do a little rearranging here. We're going to divide both sides by this here, since this expression here is multiplied by this factor here. We're going to divide that out of both sides. So let's do that. And that goes away. And I think I'll bring it over here so we have a little more room. So when you take this number here, divided by this one, again, not round yet, we get negative 17. Wait a minute. Do a quick math check there before I tell you something wrong. I don't think I want to do that yet. Let's see. 2.06 for 2, 6, 5, 8, 205, 1, 2, 8. Exponent -4. Yes, that is correct. Made a little mistake there. I want to make sure I get that right. So I got 16,079 .09971 equals EA over 8.31. So now we can solve for EA. Now we're setting, I got a fairly simple little algebra here to do. I just put that over 1 and we cross multiply. So I have EA equals 16,079.09971 times 8.31. And that then comes out to be 133,000 617 0.3186. And this is in joules per mole. All right, activation energy is in joules per mole. On our data over here, our data here and here, looks like the fewest number of sig figs is 3. And so we would say then 134,000 joules per mole for our activation. Normally, not always, but normally, and this is the standard unit, joules per mole. Normally, activation energy in most references is expressed in kilojoules per mole. So if that was asked of you, of course, we would just divide by 1,000, remove the decimal 3 places. To the left would be 134 kilojoules per mole. That's not a necessary calculation unless, of course, you're asked for that. Okay? So that would be the activation energy that is required for this particular reaction to occur. All right? All right. Now, there is another way that you can determine activation energy. It's a little more cumbersome than using the Arrhenius equation. I would definitely say the Arrhenius equation is my method of. I'm going to show you how energy can also be determined graphically. All right, so we're going to do a little graphing here. So the graph of ln k versus 1 over t results in a straight line. So this is this, and this is our x-axis. ln k versus 1 over t results in a straight line, and the slope of the line is equal to the opposite of EA over R. All right. So the slope of the line is equal to the change in y over the change in x, which in this case is the change in the natural log of k versus the change of 1 over t. So let's look at how we determine activation energy graphically. Okay. So in this example here, the following table shows the constant for the rearrangement of methyl isobutane at various temperatures. All right, organic compound. Calculate the activation energy required for this reaction. Okay, so basically now, let's take a quick look at this. What order reaction is the basically this is a decomp reaction. A methyl isonitrile. Well, look at the rate constant unit, seconds to the -1. All right, well, there's only one exponent there, and the absolute value of that exponent, of course, is 1. So apparently this decomposition is a first order reaction. Anyway, based on what we've learned previously. So let's look at our data here. So we have 4 data points now that we will ultimately be graphing. But remember, we have to graph ln k versus 1 over t. So we pull some numbers on this data table that we don't have yet. So let's do first things first. Let's get these in Kelvin. So we'll add 273 to each of those. And so make a little column here. So this would be 462.7 K. Next one, 471.9 K. Next one, 503.3 K. And the last one, 524.2 K. Okay, that's temperature in Kelvin. On our graphing, we need to graph 1 over T. So we're going to need another column here of 1 over T. So basically, divided by each of those. And I'm going to stick, since we have 3 sig figs as our fewest here in our data table, I'm going to go ahead and just do that now, because when we graph it, we're not going to be able to go out an unlimited number of decimal places anyway. So I'm trying to shorten this a little bit. So 1 divided by 462.7 is 2.16 times 10 to the -3rd. Next one, 2.12 times 10 to the -3rd. Next one, 1.99 times 10 to the -3rd. And the last one, 1.91 times 10 to the -3rd. So this is 1 over t. This is going to be our data points on our x-axis. All right. Now, for our y-axis, we need to plot natural log of k, or ln k. So here we have the value of k, the rate constant. We're going to do ln k. So the natural log of each of these numbers. But again, I'm just going to hold them at 3 sig figs to simplify things for us when we graph them. Because ultimately, based on the data, we're going to go 3 sig figs anyway. So anyway, -10.6, the natural log of 2.52 times 10 to the -5th is -10.6. The next one, -9.86. Next one, -7.37. And the last one, -5.76. So there are our numbers. Make sure you have those written down. We're going to go on to the next page in our notes, which is the graphing. And then we will come back to this page and do our slope calculation and our calculation of activation energy based on that slope. So I'm going to go ahead, hopefully you got all down. I'm going to pull up the graph, which is on the next page. Yeah, there it is. Go ahead and erase this. So let's look at our graph. So here again, on our y-axis, we have ln k, and in our x-axis, we have 1 over t. T, of course, in Kelvin. Notice when we did 1 over t in our data table, I put them in scientific notation rather than decimal form. I did that for simplicity's sake, rather than having to write out a bunch of decimal numbers, which I went ahead and did for you, just to see what they were. But as you can see, it's a lot easier plotting those numbers in scientific notation form, and just noting that each of these numbers here, 1.90, 1.95, etc., are all times 10 to the minus 3. Just makes it a little easier to graph using scientific notation numbers rather than the longer decimal numbers. So we have 4 data points to graph, right? 4. And so now we're going to do that. So as I look back at the data, our first data point was whereby ln(k) was negative 10.6 and 1 over t was 2.16 times 10 to the minus third. So 2.16 times 10 to the minus third is about right there, and negative 10.6 is about right there. Is it exact? Of course it's not. Graphing, of course, is about the most subjective thing you can do. And so, no, it's not exact, but hopefully it's close. So this is data point 1, all right? Data point 2 was where ln(k) was negative 9.86 and 1 over t was 2.12 times 10 to the minus third. So 2.12 is about right here, and negative 9.86. Here's 10, 9, 5, 9, about right there, give or take. About right there. So here's data point 2. Next one, data point 3 is where ln(k) was negative 7.37 and 1 over t 1.99 times 10 to the minus 3. So 1.99 times 10 to the minus 3 would be right there, and negative 7.37. So 7.5. About there. Here's data point 3. And our last one, data point 4, is where ln(k) is minus 5.76 and 1 over t is 1.91 times 10 to the minus 3. So 1.91 is right there, negative 5.76. 5, right there. So there are our 4 data points. So when finding slope, of course, using graphical data points, we don't draw a zigzag line. We're not playing connect the dots. We want to draw a best fit line. Best fit. So based on those, let's see. Not too terribly bad. They're not the greatest. Oh dear. Yeah, well, that's what happens. There we go. Not the greatest line for sure. There we go. And again, I could draw those data points 100 times, and I'd probably get 100 different lines with 100 different slopes. So there again, that's the subjective nature of graphing by hand. So what I'm showing here is a little different than what I showed in my notes. There again, some subjectivity there. But I'm just going to go based off what I have in my notes, so my numbers match up with what you guys have on your keys. So I made a little note here that when I did this originally, that actually 3 of my points, points 1, 2, and 4, are all on my line. All right. So just pick 2 of those points to calculate slope. Now, so here on this particular line, which I probably didn't draw the greatest, this should probably be on this side, or this one should be, drawing it more accurately. I'm showing points 1 and 4 on my graph here. In my original one that I did in the notes, I actually got 3 of the 4 points on the line. All you need, but you should know, all the number of points you need to determine slope is 2. And by chance, if your best fit line only incorporated 1 of your data points, which is entirely possible, or none, that's possible too. It could have been, lying on either side of all 4 of them. Just pick any 2 points on the line to determine your slope. It doesn't matter where they are. It could have been here and here. It doesn't matter. Just make sure you have 2 points that are exactly on the line when determining slope. So what I ended up doing was I used points 1 and 4 in my calculation when I did this originally. So that's the 2 points I'm going to use now to demonstrate that for you guys. So let's go back to the previous page. And now we can do the math. So again, I use points 1 and 4. So this one here and this one here. Of course, I have what we did here erased now. Hopefully you still have that. So the slope then of the line is the change in y over the change in x, which is the change in ln k over the change in 1 over t. All right. So we use points 1 and 4. So point 1, and it doesn't matter if you take 1 minus 4 or 4 minus 1, as long as you do them in the same order. It won't matter. So I use point 1 first, which was negative 10.6, minus point 4, which was negative 5.76. So there's my change in y. My change in x for those 2 points correspondingly was 2.16 times 10 to the minus third minus 1.91 times 10 to the minus third. And so in doing that, I get negative 4.84 over 2.50 times 10 to the minus 4. And so my slope then to 3 sig figs came out to be negative 19,400. And notice that slope is negative. And if you remember what our line looked like, it most definitely had a negative slope. So no problem there. Okay, now to determine the activation energy graphically, the slope of the line is equal to the opposite sign of EA over R. So our slope is negative 19,400 equals negative EA over, again, R. We use 8.31. So put that over 1 and cross multiply and divide. The negative signs, of course, will cancel out. We have EA equals 19,400 times 8.31. And to 3 sig figs, again, based on our original data, that comes out to 161,000 joules per mole, which is the correct answer in the standard unit. Again, if it had asked for kilojoules, 3 sig figs. If it had asked for kilojoules, which did it? No, it did not. But just FYI, if it had, it would have been 161 kilojoules per mole. Okay? And that is the way that you determine activation energy graphically. Like I said, if I had my preference, I would go with the Arrhenius equation. But certainly, if you were collecting data in a lab and graphing it, you could certainly do it this way as well. I wanted you to see how it's done this way, basically because either in AP or in College Chem, you would be required to know how to do that. So I wanted to make sure you were exposed to that. So that finishes today's lesson on activation energy. This actually finishes our lesson in Unit 12.1 on kinetics and reaction rate. So this is Mr. Keister signing off for now, and I will catch you on the next lesson, whereby we will begin the final unit of the semester in Unit 12. That would be Unit 12.2 over equilibrium, which is very, very much related to kinetics and reaction rates. They pretty much go hand in hand. So I will sign off for today. I'll catch you guys next time, and keep working diligently on your studies. I know it's tough with e-learning. It's a whole different deal for all of us, believe me. But we'll press on and do what we need to do and get you where you need to be academically in regards to your chemistry knowledge. So until next time, catch you then. Take care.